welcome Michel Louge from Cornell to give our first keynote talk of the conference. So please, Michel.
Well, thank you very much, Ricky. Can you hear me in the back? Everybody's okay. I underwent to come to Cambridge with some trepidation. The invitation of the organizers was wonderful, but I have not contributed significantly to the subject of dense granular flows for a little while, on the order of 5 to 10 years. Nonetheless, I was hoping to summarize a few things and come up with a presentation that would spark discussions, perhaps even controversy. And so it's in that spirit that I present to you this work on dense granular flows down inclines. This work has been done in collaboration with several of you, and in particular I've enjoyed working with the University of Rennes for some time on the subject. The work that I've been doing lately has been sponsored by the Qatar National Research Fund. This is a country that has a problem with deserts, obviously, and that is interested in granular media in general and desertification in particular. So the talk will be short on mathematics, despite the Newton Institute of Mathematical Science, and hopefully will spark discussions. Obviously, granular media are important to a whole number of industrial processes and to geophysical systems. Here is Alexandre Valence dumping some sand on an incline. I'll talk about that experiment a little bit later. And here again, Alexandre Valence and Olivier Artière in a sand dune in the Qatar desert, doing some measurements of strain using the geodetect system on the avalanche face of the sand dune. So here's a typical avalanche face. This one has been created by somebody stomping, and you could see, of course, the grains going down. And here's a more spontaneous kind of avalanche that occurs on the downwind side of a dune. So there really are a number of dense granular flows that exist in nature and in industry. And one thing that I would say that perhaps will sound controversial is that in many cases we've been simplifying the problem to systems that may not necessarily be of either natural or industrial relevance. Nonetheless, a lot of progress has been made. And in order to set up the problem, I will start simple. Many of the systems that have been looked at were of a steady and fully developed nature, fully developed meaning that they no longer depend upon x, the direction of the flow, and they no longer depend on time, which of course simplifies the equations. The convection terms in the equation, the inertia disappears, and we're left with a simple force balance. So if one looks at the stress tensor in the direction of the flow and looks at the shear stress S and the normal stress perpendicular to the surfaces of the direction of flow, one defines a pressure, a granular pressure N. In this case, this is general. It doesn't depend upon the constitutive laws. For instance, you recognize here what every scuba diver experiences when going down a swimming pool. The pressure goes up with depth. Similarly, a force balance of this kind occurs in the tangential direction. And when one integrates that equation based on the boundary condition, which is well known, which is the surface, where the shear stress and the normal stress both are zero at the free surface, then one comes up with this, which immediately indicates that the effective friction, which is the ratio of the shear to the normal stress, exerted at every level of that flow is constant and equal to the tangent of the angle of inclination, which means that experimentally we have the capability of setting up the effective friction at a given value and therefore look at how the system reacts in order to adopt that effective friction under SFD conditions, steady fully developed. So then when one puts in a constitutive law, for instance, for a Newtonian viscous fluid, this well-known constitutive relation, then one can integrate this subject to a boundary condition of a zero velocity at the base, and then arrive at a quadratic profile for velocity, and therefore integrate that again to come up with a mass flow rate that depends on the cube of the flow height. So that's a simple calculation that you could give to any undergraduate. If you choose another constitutive law for the fluid, in this case, you imagine this is a turbulent fluid where the inertia of the fluid is paramount, then in that case, the shear stress at the base, which again has this form in general, upon integration of the equation that you saw in the previous slide, you then say that the shear velocity U star is typically 5% of the bulk velocity in the flow. Then when one comes up with this constant, one integrates the whole thing to a mass flow rate that now depends upon the 3/2 power of the height. So what about granular flows? Olivier Pouliquin, obviously here in the audience, came up with a seminal piece of work. In this case, he took some grains that he flowed down a chute that was prepared at the base with a rough, bumpy, as it's called, boundary, and published this very important paper in 1999. So this is a picture I took of Olivier in his lab, and I'm happy to see that he hasn't changed. What Olivier found out was that the flow could not exist at every angle. There was a minimum angle at which the flow would start, which is around 20 degrees, say, and then there were, well, no measurements, but when the angle is too large, then the steady fully developed condition can no longer be satisfied. And some people here in the audience have worked on accelerated flows that have very different character. But what Olivier found, which was rather remarkable at the time, was that there was this function h stop that indicates that the flow cannot exist at any height at a given angle. If it's below that height, then the flow stops. Olivier pointed out that the dimensionless number that governs the flow, that makes the mean velocity dimensionless, could be constructed with the shear stress, rather the normal stress at the base, which of course is also given in terms of the height. And then he plotted the Froude number, this Froude number, as a function of h over h stop. That collapsed all the curves. All the angles would collapse on a single curve, which he found to be the straight line. So he found a Froude number proportional to h over h stop, which when integrated for the mass flow rate would then provide a 5/2 power of the height, in contrast with what we just saw for the other cases. Now, some people later argued that DeBuff and co-workers argued that in fact it wasn't so much h over h stop, it should have been h over h stop minus 1, but I suppose it may be in the eyes of the beholder. I would say that Olivier's data was better fitted by the other expression, but that's perfectly fine. The distinction is not perhaps all that important, although you will see in a moment in another flow where that distinction is important. Well, so this flow over bumpy boundaries became the hallmark, if you like, a rather generic flow that everybody wanted to explain. And I think it's fair to say, although as I mentioned earlier, I have not worked in this field for a little while, I think it's fair to say there are still mysteries in that flow. But let's take a look at what Leo Selbert came up with numerical simulations of large-scale systems in that flow, albeit with sidewalls that were pretty close. Some people, particularly in Rennes, have since made the sidewalls farther apart and realized that there are such things as recirculating flows inside that the simulations of Leo Selbert didn't have, because there were no sidewalls that are periodic in the direction perpendicular, in the third direction, but the rolls could not arise. Nonetheless, most of the physics that was observed in experiments was also found in the simulations. So if this is a bumpy boundary, the flow existed only in the range of angles. Crucially, what really excited people was that the volume fraction in the core, in what I call the core of the flow, which was far enough from the bottom boundary as not to be influenced by the bottom boundary, and far enough from the free surface so as to be away from the region where you basically have a very dilute gas, granular gas. In that core, the volume fraction was roughly constant to an arbitrary precision, if you like, that was determined by the simulation or perhaps the experiment. So, of course, Leo Selbert confirmed that dependence of the mean velocity that Pouliken had come up with, and again confirmed that D was as a h to the 5 half power of the mass flow rate. So a lot of people then said, well, let's try and model this. And of course, a great candidate for that modeling was to take a look at the kinetic theory of dense gases. Ogawa had years ago had come up with the concept of a granular temperature, which resembles the temperature of an ordinary gas. And then Jim Jenkins and Stuart Savage and Lund later and had a number of papers that laid a very firm foundation of the role of the granular temperature in similar to what the Maxwell and Boltzmann had pioneered. So this is an experiment where one of my students, Michael Adams, years ago did on the KC-135 microgravity aircraft. So this is called a free float. And you've got a camera looking at these boxes, and this is two of the boxes we're just testing, seeing whether electrostatics would affect one of our microgravity experiments. And so this just illustrates the concept of a granular temperature. So in turbulence, you would call K, except K is would basically be 3 hops of this trace of the velocity fluctuation second order moment tensor. So it's like the temperature in ordinary gas. And then, so Jim Jenkins and Stuart Savage came up with some formal calculations through a series of papers of the transport coefficients that the temperature endows to this fluid. In particular, there's a viscosity, which, like an ordinary gas, depends on the square root of the temperature. There's a conductivity of this pseudo energy, if you like, and then, unlike in ordinary gas, there's a volumetric dissipation rate that can be calculated that goes at the 3/2 power of the temperature. Just like when you write the K epsilon model in turbulence, you have terms of the equation of dissipation that go as K to the 3/2. They have exactly the same origin. And then, of course, there's an equation of state, the PV equal nRT of dense gases, yet modified for the fact that these particles are much more densely packed, and therefore these functions, F1, F2, F3, F4, are dependent on the volume fraction of solids and the pair distribution function. There's also an entire field of endeavor that endeavors to look at the form of the pair distribution function as a function of volume fraction. And of course, as one goes closer to the glass transition, to jamming, these pair distribution functions do diverge in different ways. There's hysteresis involved. So it can become rather complicated when it's dense. It's much easier when it's dilute, although there are, of course, challenges such as anisotropies and so forth. But when one goes close to the dense packing, there are effects that are undoubtedly important in the dense granular flows that may play an important role, and it's not altogether clear what even the pair distribution function at contact with the boundary or among the particles looks like. People like Torquato, for instance, have been very famous in trying to look at these issues. Okay, so in having the transport coefficients, what I would call a kinetic theory cartoon can be put together. So it goes like this. It's a similar kind of reasoning as what I showed you earlier for a Newtonian fluid. This equation here is really independent of the constitutive law that one could adopt. In this case, the constitutive law looks like this transport coefficient that has inside this viscosity with the granular temperature in there. So one has to solve for the granular temperature in order to close the problem, similar to solving for K in turbulence in order to close the problem. So in this particular case, it's nice in a flow like this because the normal stress is known as a result of the integration that I showed you earlier, and because it is related to the equation of state to the temperature, then one knows what the temperature is, and it roughly goes linearly from the free surface if you exclude what happens at the top boundary and at the bottom. So that equation of state, you can combine the two equations, and then again, if you're willing to assume that there's a no-slip condition at the base, which may or may not be true, because after all, a granular medium does not necessarily indulge you in having a no-slip velocity at the base. Sometimes it has to be calculated from the boundary conditions in ways that Jim Jenkins actually worked out. Can I take questions during the talk?
Yeah.
Great, please.
Why do you assume the temperature is constant throughout the flow?
It's not constant. It goes linearly, roughly linearly with depth.
So you wouldn't want to necessarily have a dynamics to that as well?
Oh, there is. And in fact, I'll talk about that in a moment. Thank you. Yes, of course. So the temperature, if you like, grows as y, if you assume this cartoon. Okay? Yeah, thank you. So this integration then leads to, once you combine these two equations, indeed leads to what people have called the Bagnall profile, in homage to Ralph Bagnall, of course, very well known, fluid in the mission at Cambridge. Lots of Cambridge folks have had their hands on this problem. Called the Bagnall profile because Bagnall was the first to realize that one could solve a conundrum by assuming that there was a fluctuation velocity in the granular medium, and therefore the singularity at the, for instance, at the symmetry axis of a pipe flow could be lifted. So in his name, it's now called the Bagnall profile, although Bagnall, to my knowledge, did not work on this. One interesting combination is in a number that is called I, and I'll talk about that in the next slide, that appears naturally in the relation of the velocity to the spatial profile. Again, can be integrated, and lo and behold, one comes up with a 5-second power of the height. Okay, so the inertial number that was proposed by François Chevois, Olivier Pouliquin, and others, others shown here, is a way to relate the effective friction, that is the shear of a normal stress if the flow is SFD, so if we develop, in terms of that inertial number, sometimes called the Savage number or the Bagnall number or the inertial number. And what they proposed was something that sounded quite natural, that the effective friction would be related to this number, and it has been a very useful way to, very insightful and useful way for people who have flows of practical interest in industry, in particular, to come up with an answer. It's really not that trivial to work on granular media. One cannot wait for all the theories to be closed and all the dots to be put on I's and so forth until in order to solve this. Okay, so is the problem solved? And I'm happy to report that for the sake of our employment, the problem is probably not solved. But if the problem had been solved, it would have resembled people after Osborne Reynolds did famous experiments on pipes to show the transition to turbulence. At the time, people could have said, oh, everything in fluid mechanics is now solved. All we need to do is to define the Reynolds number, and here's the friction coefficient that really resembles this S over N effective friction. And we could just empirically come up with the relation for this and be done. And yes, some people, of course, use those graphs and that's how they do their calculations. So now what I would like to do is I would like to talk about a number of issues that I think deserve a little bit of attention. And I will begin, again, rather simply by pointing out that flows can have very different concavities of the velocity profile versus depth. This is something which surprisingly to this audience, because we pretty much all know this, but I've seen practitioners use an approach which was inherently designed for flows of a concavity of a 3/2 power that I showed, use it for flows that have a completely different concavity and in fact a completely different physics. So it's important to point out. So going back to a viscosity, which in this case of granular medium is no longer a constant like it is in a Newtonian fluid, one can very simply show from this equation, which is correct in steady fluid flow no matter what, can be differentiated with respect to the distance from the free surface. And here's this grouping. I mean, it's really nothing to write home about, but if the concavity is negative, which is typical of the Bagnall profile, negative because the y starts at the free surface, it's where it's most natural to start the origin of coordinates, not at the bottom, then in that case, it's a necessary and sufficient condition to have this relation among the differential, the logarithmic differential of the viscosity and the logarithmic differential of the volume fraction. So for a bumpy base, what is it? Well, it's the logarithmic dependence of the viscosity is exactly 1/2 in the Bagnall profile, and the volume fraction is a constant. So in a bumpy base, basically what we have is we have a rather moderate increase in viscosity with depth, and it is in the case where the flow is what is called so-called core flows. So that's what is relevant for the so-called Bagnall profile. However, there are plenty of other flows, and in fact, one may argue that in geophysics, for instance, these other flows are way more important than the flows over a hard boundary. And one may also argue, and there's some experimental evidence for this, that as a flow becomes very deep over a bumpy base, then instead of having a Froude number that rises with the height, actually it becomes a constant Froude number. There's a bit of an asymptotic effect there, in which the Froude number then becomes constant, and I'll talk about a regime where the Froude number then becomes a constant. So it could be that in most flows of geophysical interest, such as dense flow avalanches and such, it is very rare to see a flow that behaves with a 3/2 power of the height. And here's an example. Renaud Delaney and his co-workers in Rennes, many of them are here, were quite surprised to see that if you confine a flow within two sidewalls, then the sidewalls will participate in holding the flow, if you like. And as a result, one obtains, as long as it's dynamic, as long as the flow keeps going, then the flow can achieve inclinations that would not be expected, that greatly exceed the angle of repose of a heap. And they call that the superstable heap, or also known as the sidewall stabilized heap. So this angle theta, actually I called it alpha elsewhere, but forgive me. This angle can be much greater than the angle of repose, but there are sidewalls that hold the flow. And these are simulations by Nicolas Taberlet, who's also here. And clearly the concavity of the velocity profile is very different. It's almost linear near the free surface, and then it is asymptotically very, very, very slowly. In fact, so slowly as to, there have been some measurements of using diffusion wave spectroscopy that were capable of measuring extremely small displacements of the velocity of the grains deep in the pile. And it turns out that nobody has seen the bottom of this. In other words, there's always some micro rearrangement deep enough in the pile, and you could go on and on and on. And there's a remarkable measurement that was done in Rennes where there were if I can remember how many, but something like 6 orders of magnitude, 6 decades of velocity resolution, and from the free surface all the way down, and they could not see the end. So clearly this profile does not have a zero slip, that's strictly speaking. And interestingly enough, the volume fraction goes from literally the Maxwell, if you like, it's this profile of volume fraction. This is basically a gas, a dilute gas, can be calculated, and it's actually, from the simulation, can be quite easily related to the granular temperature at the top of the flow, just like the famous Maxwell calculation. But then it keeps increasing asymptotically to a jamming volume fraction in the pile, and having very small rearrangements again that are consistent with cage diffusion and things of that nature. So there's really something interesting going down there. And in this case, in the scheme of things, in the equation that I showed you earlier, the inequality, if you ignore the sidewalls, and forgive me for this, but I'll show you a flow in a moment that does not really have sidewalls that has the same character. But if you were to ignore the sidewalls, which of course are an important aspect of the momentum balance, but you would show that that concavity means that if, in fact, and particularly if the volume fraction increases dramatically from the free surface, then the viscosity has to increase even more dramatically. So no longer than 1/2, but it has to be way larger than 1 in order to be consistent. So rapid increase in the volume fraction and rapid increase in the volume fraction with depth. So it is rather impossible, in fact, one can say, to fit a shoe that's, let's say, a size 5 into a foot of size 10. That is, none of the flows of Bagnolian-like flows that we talked about has anything to do with this, not too surprisingly. Okay, so you might say, well, what about the sidewalls? Well, the sidewalls are not necessary in order to have a concavity of that nature, and Alexandre Valence and I recently in Rennes a few months ago did a very simple experiment that was the prelude of the experiment we wanted to do in the desert with the geodetect system, where we measured strain in the avalanche of a sand dune as a function of depth and time and over several days. And in this case, we just put the same geotextile, used a lot in the civil engineering industry. We laid it down on the base of the chute, and it sort of resembled the Dayer and Douadi experiment on felt that was done at the time that was relevant to what happened at the avalanche face of a dune, where there's a propagation of waves either going up or going down. But in this case, we want to have a similar system, except fully developed and steady, and where the sidewalls were no longer as important as they were in the sidewall stabilized heap. And so we just tried that, and it turns out that the sidewalls played very little role, as evidence from measurements of the flow from the free surface. So now what you have is you have a base that is very soft and very dissipative of the granular temperature and the fluctuation kinetic energy. All right. So if one comes up, so if there was any need to bolster the statement that I made earlier on the irrelevance of the scaling that of the mass flow rates to the height to the 1/2 power, the 3/2 power versus h over h stub minus 1, one could just look at that curve, and if you take the same data points, you can see that it works a lot better. And so in this case, the mass flow rate is proportional to the flowing height, which is h minus h stub over h stub here, directly to the 1 power, okay, as opposed to the other exponents that we talked about earlier. And the relevant length scale being the particle diameter in this case. Now in the case of you remember the case of the sidewall stabilized heap, the length scale that was relevant was not the diameter, but the width of the flow. And so here's to show this. Here's some experiments that we did at Cornell on a similar sidewall stabilized heap with help from our Rennes colleagues. And so this is the tangent of the angle of inclination as a function of a height over the width ratio. This is what they found over different ratio of the width over the flow over the particle diameter, spanning a fairly large range from 4.5 to 22. So those are collapsed reasonably well to this expression that simply tells you that the angle of inclination, the effective angle of the effective friction, or the tangent of the angle of inclination, is some sort of a minimum number plus the contribution of the friction from the sidewalls that holds the flow down. Of course, as the height goes up, that contribution of the sidewalls goes up and therefore is capable of having a much steeper flow. Yes, please. Sorry.
You started by describing the velocity u as a function only of distance y, which was depth from the surface. But now you put in sidewalls, does not the normal coordinate to play a part?
Of course, it plays an important part. Yes, this is also average. Excellent question. Thank you for asking. It's this is averaged over the width in this case. Yes, totally wonderful. This is basically a control volume with the entire width.
Just a related question. I mean, the concavity has to be taken both ways.
What do you mean?
Both width as well as height.
Oh yes, absolutely. This is an averaging similar to the averaging in the Savinon equations or the boundary layer.
So the concavity relation you showed may not actually be true.
Correct. In fact, this precisely. And thank you. And yes, strictly speaking, the relation that I showed with the viscosity is relevant to the flow where the sidewalls are far away, and that's why we did that experiment, because clearly that wouldn't have been the case in the SSH. However, interestingly enough, there is a relation between the two, in which this was the SSH, the sidewall stabilized heap, where width is the length scale. Now, when the sidewalls are thrown to infinity, if you like, now that length scale is no longer available, and the diameter replaces it. So it's not all that surprising, if you like, that we would have a morphing of the mass flow rate versus flow height, that would involve different length scale, because now there's no sidewalls. Okay, so all right, but the point is that the mass flow rate now is the first power of that flowing height, as opposed to the other exponents that we talked about earlier. Okay, let's talk now about the flat frictional base. That's something that is of great industrial relevance. I don't think I've seen any chutes that is bumpy base in industry. They don't want to slow down their chutes. They want to make the chutes go as fast as possible. And obviously on a flat base, it's sort of intuitive. It should go faster. So these are simulations by Nicolas Taberlet, again, that I showed earlier some of his other simulations. So this is a bumpy base and a flat frictional base. This is the velocity colored. Okay, and so here's the profile on the bumpy base, the profile we talked about earlier, the Bagnolian profile. On a flat base, clearly is much greater, as everybody in industry knows. But what's rather interesting is if you translate the velocity profile in the bumpy base, you will see that in the core, what I call the core of the flow on the flat frictional base, it is totally parallel, which means that there really is a Bagnolian profile over the flat frictional base, but it is above the boundary. And really what happens is that there's a large slip at the bottom of the flat frictional base that really is what characterizes the flow. And that large slip can be basically the large slip is what will determine eventually the mass flow rate, and one could even ignore the fact that there's a Bagnolian profile above while you do the integration. It is the large slip that dominates the mass flow rate and not the Bagnolian integration. Again, there is also a core, and the volume fraction Nicolas Taberlet showed that is the same as the one over the bumpy base. There also is a core, and it rejoins the same volume fraction. So the flows are cousins, if you like, but one is much faster than the other. Okay, so here's another kinetic theory cartoon on that flow in the flat frictional base. So similarly, one can calculate the granular temperature at the base. So now focus your attention on the subscript 0, which indicates that now we're looking at what happens in the basal layer, which governs the slip and which in turn governs the mass flow rate. So it adopts a certain volume fraction, nu0, and a certain temperature. The temperature, you can come up with it from the same combination of equation of state and an integration down to the free bound to the bottom boundary, then the same kind of calculation of the shear stress can now be related to the gradient of the velocity at the base, which now becomes, roughly speaking, if you simplify the Bagnall profile to being a constant velocity, and if you ignore, if you just say that the gradient velocity is over a very thin basal layer, you then have an estimate of that gradient. And I need a little bit of water, otherwise my voice can go up. Sorry. Okay. Okay, so now the basal quantities combine. And the cartoon gives us a Froude number, which now is a constant value, only a function of the angle of inclination. Once again, this is a kinetic theory cartoon. And I'll mention in a moment why it probably isn't quite right. But it has the right scaling. In this case, the Froude number being a constant, remember the Froude number was increasing with height in the Bagnallian flow. Now it's a constant. And so as a result, the mass flow rate now grows as the 3/2 power of the height. Okay, the length and the reason for this, really the ultimate reason in the basal flow like that, is that the length scale is no longer the entire depth of the flow. It is now the diameter, which is on the order of the thickness of that layer at the base. What you essentially have, whether you are in a Bagnallian flow and you have a flow that is sheared all the way to the boundary, or this, there is a region right near the base where the flow feels that the base is there, and in solid mechanics, they would call that a localization, essentially a localization of the phenomenon that is only a few grains thick, on the order of 5 to 7 grains, and that's what one observes in the basal region of a Bagnallian profile, and as well as this localization does occur here as well. Okay, so experiments to boost this up. These are experiments I did with Steve Keast back in the mid to late 1990s. So it tells you how long ago I've been worked on this problem. I'm sure you'll straighten me out on all the things that I've missed since then. So the way to model this simply is to say there's a passive overburden, which is the Bagnallian profile, becomes much less important, so I treat it as a passive overburden. This was an idea that Jim Jenkins mentioned, and then whoops, this thing is giving up. No, here it is. And some sort of a basal layer that they can be modeled. Now, Roy Jackson was one of the first people to work quite seriously on both the flat frictional and the bumpy boundaries. There's a number of papers that were written. Stuart Savage also did contribute. There's a number of authors. And what Roy Jackson pointed out that all the flow experiments could be put in a diagram, in a single diagram that shows the mass flow rate in terms of the mass holdup. So you see the mass flow rate is the integral of the velocity profile times the volume fraction, and the mass holdup it goes as the integral of the volume fraction. And so the flows at different angle of inclination can be and at different heights, if you like. These are 16 degrees, different heights, can be represented, and it can be shown that that indeed the Froude number is a constant and no longer dependent on the height. Okay, so what is the challenge in flows of a flat frictional wall? It's to predict what happens at the base, and clearly that is not being predicted. Charlie, you had your hand up.
Trying for about 5
I'm sorry, it's like waiters in a cafe. You can never get their attention. Sorry. Okay, go ahead.
Well, it just occurred to me that you keep talking about the slip layer in terms of granular temperature and kinetic theory.
Oh yes.
Isn't the simple answer that you've got a rolling layer of particles?
Aha, thank you very
Are
much.
seen in
So
simulations going back
Charlie's great. He's
30 years?
Totally, 30 years. Oh yeah, yes. In fact, Charlie is literally, understands this very well and is perfect
That
segue
gives them 30.
into what I'm talking about in this slide. So this is great. Charlie's talking about the rolling layer at the bottom. So this is what in fact, what this
You're
slide
about
is
to
about.
get to?
Yes,
Oh, okay.
absolutely. It shows that you're great. Yeah, absolutely. Thank you very much. So we do have, again, this tangent of alpha, which is the effective friction. And the argument is here that because if you ignore the sidewalls, because all forces are exerted at the point of contact of individual grains with that flat wall, geometrically, that's an argument that's a bit incontrovertible, it's right at that point, it means that it is the dynamics of that point that matter. And here's the conundrum that we have. We took pains at measuring the friction angle of these beads, these glass beads that were glued on a piece of metal, and we put it on the chute, and we raised the chute until the friction was such that the tangent of the angle of inclination exceeded that friction, and it started slipping. So that was 0.59, pretty large value. And then we had a facility where we studied impact that allowed us to do some impact measurements of either particles colliding in midair or particles colliding with walls. In this case, with the very same particles, we on the very same surface, we measured 0.14. So two very different values of friction. And it turns out that over the range of inclinations where we observe steady fully developed flows, which is this range of angles, it turned out that range of angle was somewhere between the arctangent of these two numbers. So there was a bit of a smoking gun, if you like. Being in the US, I use that kind of analogy. In that the effective friction was adjusting itself to an angle that was exactly equal to the angle at which the chute was held. Otis Walton we did numerical simulations, had actually seen that conundrum before. He did some numerical simulations and realized for quite a while that if one adopted a single friction, one had to raise that friction to values that were totally unphysical. And why is that? It's because if you have a single friction coefficient at the point of contact, then the ratio of the tangential to the normal force had to be, by Coulomb's law, the Coulomb's law says less or equal to mu, meaning that by the time you integrate all the interactions of all the grains with the bottom wall, you could only have an effective angle of that integration that was less than the friction that you assumed. So that was a bit of a conundrum. And many simulations have the same conundrum. They use a friction coefficient which is artificially too high, which is completely and thoroughly unphysical. There's no, to my knowledge, there's no impact friction with this kind of experiment here that is of no simulation ever assumes this. They always assumes that. Okay, so the point is that the friction probably adjusts itself to the speed, the speed of the contact point, the relative speed of the contact point with the base, and that's well known. Friction is a complicated system. It's a dynamical system. Bomberger and Caroli, for instance, wrote a series of seminal articles on the subject back in the 80s. Friction is not a constant. It is everybody who plays the violin knows that there's a regime of stick slip which gives rise to sound. Steady friction is only a part of that regime. But Ken Johnson, here in Cambridge, has known that for many years. Okay, so that's okay, so Basel rolling, thank you. It wasn't this slide, it was the next one. Effective friction, the effective friction I'm talking about here is actually set in our view by Basel rolling. So so this is some theory that we put together that appears in that Physics of Fluids article of the effective friction as a function of Froude number. And so here's the value of the enduring friction, we called it. And here's the value of the impulsive friction due to impact. And if one comes up with a theory that marries an enduring kind of theory a la Jackson, Roy Jackson was the first one who actually put together a tensor, added the two tensors together, one that dealt with enduring forces, more like solid mechanics, together with a tensor that looked more like the kinetic theory of dense gases. You added them up together. It was a bit controversial to do that, but why not? We adopted the same formalism. Stuart Savage also did that. And we calculated formally that the effective friction had to go down with the Froude number, which of course was a conundrum because it led to an unstable flow. There was no way, if you make your friction less if you go faster, then clearly it's conditionally unstable every point on the curve. Okay, so we had that conundrum, but the rolling layer was the one that let us go above that conundrum. Imagine you are driving a truck, and instead of having the wheels of your truck be fixed like they are, okay, now the wheels are able to collide with one another at a frequency set up by the granular temperature. In this case, the analogy is not very apt, but so if the wheels of the truck are allowed to collide, then clearly they will break upon each other. They will move upon each other, and that's precisely what happens in the basal layer of an inclined flow like that. There is a granular temperature at the base, and it governs the rate at which these wheels collide. And as soon as they collide, they will dissipate what? Well, they will dissipate what makes them flow, which is the rotation rate, the rotation of the wheels. The wheels will break up, and at every collision, there is this balance between the production. There's a production of angular momentum, if you like, by the if you take the brakes off on your truck, you will keep rolling down all the way down to downtown Ithaca, I suppose, on Buffalo Street. But if now you allow your wheels to collide, then clearly there's going to be a dissipation of that, not a dissipation, but a reduction, if you like, per unit time. And it is that balance. Once you write that balance, which depends on the collision frequency of the wheels, which depends on the granular temperature and the local volume fraction, it is that balance that sets up the volume fraction at the base. And if you write that, you then calculate what the volume fraction at the base is, and then you come up with that orange line, which turns out to be rather well representative of the experimental points at constant Froude number that we found. So now the problem is no longer unstable. You do have waves that can develop. You can actually write a stability argument, a linear stability argument of the Saint-Venant equations. One can think what wants about the Saint-Venant equations. After all, they are averaged in the depth of the flow, and therefore some of the instability modes must be suppressed by that integration. Nonetheless, there are some interesting, one can show that waves will develop, and yes, indeed, in that paper we documented a number of waves that looked at graphic waves and roll waves, and also there's a whole zoology of waves that occurred in those flows, and that we documented in a rather thick paper that was just too thick for people to read, I think. Okay, so let's talk a little bit about fluctuation energy, because I think people here will straighten me out. I know there have been a lot of progress since I last looked at the problem. So you will see the depth of my ignorance of. But the fluctuation energy in steady fully developed flow, the balance looks like this. You have a, so this is what you, the first two terms is what you would see in an ordinary fluid where the Eckert number is non-zero, that is to say where the working of the shear through the stress tensor rather through the velocity gradients is contributes to the heat transfer flux. The difference here is that we now have a dissipation here per unit volume. So here's the heat flux gradient that has to do with this conductivity I talked about. Here's the flux, looks like a Fourier flux. Here's the work rate of the shearing, and here is the dissipation. And okay, so here, what is the conundrum? Well, the conundrum is that if you just assume that you have kinetic theory, and if you make the distance from the free surface dimensionless with the grain diameter, n goes roughly as proportional to y, so does s. The temperature also is proportional to y. The things I talked about earlier. And then if you put all the equations together in what I showed earlier, you get this monster thing that only involves these functions of volume fraction here, And so if you take the problem in this direction, if the volume fraction is a constant in the core, and there's no term of the flux gradient, which what Kumaran showed was negligible in the core because the conduction length was very small, right? Then you could say, okay, you then can, well, if you transform this equation to this one, but here's the conundrum. This term here is proportional to volume fraction. I mean, is a function of the volume fraction. So if indeed the equality here, so here are the terms identified. If the equality does not involve dq dy, I'm sorry. If dq dy is non-zero, then it follows that you cannot have nu equals constant because it has to depend on y, which is still in this equation. So one must neglect dq dy in order to show with kinetic theory of dense gases that the volume fraction is a constant. In principle, it's a mathematical certainty. It could be that that's an approximation, and I think it's the argument that is being put forth that is a good approximation. Okay, let's see how good. So in principle, if you approximate and say that dq dy is 0, then you get this, which means that tangent square alpha is a function of volume fraction, which means that at a given angle, you have a given volume fraction. Okay, so that's the argument. So if you go back the other way, you say, oh, well, if dq dy is 0 and t goes like this and q has to have this form, then it follows that the conductivity has to be in invariant. Trouble is, it's not an invariant in the kinetic theory because it depends on square root of t, which itself depends on square root of y, and therefore it's not working. Okay, so the conductivity, strictly speaking, mathematically, this is a mathematical institute, right? So I could say that. Strictly speaking, the conductivity must be invariant for the kinetic theory to apply. Okay. All right. Okay, so this was done a while ago. So I know that there have been some developments that Kumar, I'm sure, will tell us about that. But at the time, I bothered to take the myriad of papers that were written on the subject, and I've forgotten a few, Bouquet and PRL and so forth, and I dissected each and every one of them and I put it on MATLAB or Mathematica and integrated the equations, and I wanted to see what they predicted. You know, this was an honest attempt at looking at what was going on. So if you take the kinetic theory of Jenkins and Richmond with typical values of coefficient of restitution and give a typical angle, so this is h minus y over d, in other words, in the depth of the free surface on the right side and the bumpy boundaries on the left. And there are boundary conditions here. There are also details which I put in as honestly as I could, given what they showed in the paper. Basically, none of them predicted what was shown in experiments or in numerical simulations. Some were, I mean, it really, and particularly, there was no invariance of the volume fraction in the core. So here's the, and Kumaran was the winner of that contest at the time, and I spent at KITP. We spent several weeks together arguing. It was great. We shared the house. It was absolutely wonderful. It's another of these scientific paradises that you have here. And anyway, so Kumaran was the closest with this partially rough theory. Okay, so I then argued that perhaps if particles were in contact, maybe they would transmit energy at long distances, and so I carried out a complete calculation that people had done earlier, but I revisited that calculation in order to calculate the conduction of energy and the local dissipation that would occur as a result of the propagation of those waves. The dissipation depends upon the volume fraction, the coefficient of restitution, because every collision is inelastic. So I modeled that as a dashpot. So here's the dissipation and a spring, okay, which is simulations have spring and dashpots. But now the difference was that this was just a single column of grains, and the incident sphere was simply a sphere dropped upon it, and they looked at the waves. So this is an exact calculation, and that can be developed. So one has to make it continuous, and then one defines the speed of sound and the equivalent of diffusion coefficient. So there's a Pickley number that comes up, and I go over the details. But here's the complex variables. You can define the complex conductivity. Its real part is the actual conductivity. Its imaginary part is dissipation, just like an RNC circuit in electricity. This is a linear system, so unlike constant contact. But one can come up with the conductivity that, lo and behold, happens to be a constant. And lo and behold, happens to be much greater. If I start putting numbers that are relevant to granular flows, that conductivity exceeds by several orders of magnitude the conductivity that the kinetic theory would predict. In fact, Charlie Campbell here had a number of arguments which unfortunately were ignored by the community. In fact, we had some discussions to that effect at the last powders and grains. But anyway, the point is that it's not just impulsive contacts that might matter, although Kumaran will argue, I'm sure, that one can, by suitable further expansion of the kinetic theory to Burnett order and so forth, the late Isaac Gorthier had similar arguments, and I certainly respect all these arguments. One could come up with things that may get the conundrum figured out. Okay. All right, so let me just simply conclude. What we found, experimentally, when I say we, I mean the entire field, is that the exponent of the mass flow rate per unit width versus height of the flow can be very different in different flows. In the self-dissipative base, it's 1. Okay, you could see the diagram is quite clearly showing that 1 would work and 1.5. I'm sorry, 2.5, which is here, would not. For Newtonian fluid, turbulent would be 1.5. Coincidentally, it's the same as what happens over a flat frictional base. So the fluid number, if you like, is a constant in both cases, and which is well known to people who do hydraulics. The core over a bumpy base is 2.5, the so-called Bagnolan flow, and if this is a Newtonian fluid laminar, which of course hardly ever happens, but in flows of interest, but it's as high as 3. So these exponents really are an integrated system. It's an integral, so it's difficult to argue with it. Unlike the precision to which one would say that the flow is fully developed, the Born function is a constant. In mathematics, in physics, it's impossible to show that something is 0. There really is no way to show that something is 0. So one could always argue endlessly that a flow is not fully developed and it's not steady, and because the experiments always have some degree of, or simulations have some degree of uncertainty. Okay, so that's my conclusions. Boundaries matter, and I thank you for your attention.
Sure, there must be some questions.
I have 2 questions actually. The first one is, what is the plural of the word conundrum? Is it conundra?
I think so, yes. I remember my Latin, that's right, yes. Templum, template.
The second question is, I would like to model, perhaps because I'm from one side, I'm an engineer, I would like to model the granular flows on a substrate with 2 ingredients. On the one hand, constitutive law for the bulk flow. On the other hand, boundary law or boundary layer law, involving perhaps a few, the boundary layer would involve perhaps 10 grains or a few granular layers. And, is that, would you agree with this? And would you, do you think you can cast the various observations into that framework? Or?
Yeah, well, I will interpret that as a useful comment rather than a question. I would say definitely yes. There are approaches that, we have to use the Savonneau theory we have to use the boundary layer theory. We can't avoid it. So similarly, we have a question, but I don't know in what order. At the back. Yeah.
So maybe to follow up on this observation about boundary effects. So in some sense, it looked to me like the mathematical technique of matched asymptotics
Of course.
would be a particularly useful way to view this. And the only question that's not clear to me is whether, in fact, it's a single continuum theory which encodes all of that, or whether or not you need to actually do some statistical mechanics to derive separately effective boundary conditions. So my sort of follow-up question was, I sort of very much appreciated this rolling sphere with collisions. What's known about the statistical mechanics of that ensemble, in particular from a non-equilibrium thermodynamic standpoint? It's particularly interesting because that's a driven problem, so not necessarily leading to Boltzmann distributions.
This is a really wonderful comments. And I would say yes on both questions. Matches and methodics certainly should be used. In fact, I've argued that to make very simple, in one of the papers that was here, I made a very simple theory that was matching things, although I'm sure Cornell has something to say. He's probably much better placed to comment on this, but from my standpoint, definitely. And as far as the rotation rate and so forth, there have been theories, kinetic theories, that have included the rotation, but of course they're much more complicated. Lund, for instance, had. One also should probably consider couple stresses. There's Namiko Mitarai and Isao Yakawa did some rather seminal work on that subject. Granular media are such that the forces are exerted at the point of contact, which is away from the center of gravity. So there are couple stresses that must arise, particularly in our boundaries. The problems are complicated, and yes, definitely, it's not an easy one.
Well, maybe I just throw one other remark in, which relates to your pointing to someone over here who's interested in hard sphere, Boltzmann-like expansions. So just an observation, the last equation you put up was viscoelasticity.
I'm sorry, which?
The last equation that you put up, your dashpot model.
Oh yes, yes.
So that's viscoelasticity, linear viscoelasticity.
Definitely, yeah. It's
and so it's
was the key.
yeah, but it's known that if you take the Boltzmann equation and you start carrying out expansions, then indeed the hierarchy of equations eventually leads to a viscosity, which would be the last term you have there. So it is rationally identifiable from that.
I will defer the questions on the kinetic theory to people who really know something about it. I've been a user of the result, engineering-like, and so there are people in the audience who are really much more knowledgeable on that. Yeah.
I think Michel's being very modest. I'm afraid we don't have any time for any more questions. We have another speaker, except I have one question, and that's does Olivier still have that jumper?
No.
The jumper, the picture that Michel put up, there was exactly the jumper. I think Jim was after it. That was our next speaker. So, round of applause.